Welcome back to PV Online. Today we're going to take a look at a conservation of energy problem, but this time with non-conservative forces. And all that means is what happens if friction is involved. And so we've got an example of here's a child on a hill, let's say he's sliding down a hill. And we know that he starts up here on the top of the hill at 4.5 meters, meaning he's got potential energy at the top. And then down at the bottom, we can see that he's moving, and so that indicates that he's got kinetic energy. But what's going to happen in this case is these two terms are not going to be equal to each other. And they're not going to be equal to each other because friction was involved. So what we need to do is let's take a look at the top point right here. So let's call this at the top, and we have this down here at the bottom. And at the top, we know he's got potential energy. And at the bottom, we know he's got kinetic energy. But this time, I can't say that the potential energy equals the kinetic energy. That is not a true statement because we've lost some of the potential energy, and we lost that to work, the work done by friction. So now I want to find out how much energy was lost due to friction. So let's first start with this. Let's find out how much work was done by friction. So my potential energy is simply mgh minus the work done by friction. That's going to equal my kinetic energy, 1/2 mv squared. I can't just cancel out my masses because work doesn't have a mass term in it. So I'm going to take this 22 times the 9.8 times the height, which was 4.5 meters, minus the work done by friction, which is what I'm solving for, equals 1/2 the mass of the child, which is 22, times the velocity at the bottom of the hill, which is 2.5 squared. So let's solve for the work done by friction. And that gives me 901 joules. But the question doesn't ask just how much our energy was lost due to friction. The question is, what's the percent of energy lost? All right, our total energy came from the potential energy at the top. So let's solve for that. So let's find out how much potential energy we had at the beginning. And we had 9,702 joules to start with. So the total amount of energy that we had was 9,702 joules. We lost 901. So if I want a percent, we're just going to take this ratio, 901, divided by 9,702, which was my total. Since I want a percent, I need to multiply that by 100. And that's going to give me 9.3%. So almost 10% of our energy was lost due to friction. Okay, so in this case, we have a 5 kilogram block, starts from rest, and that tells me that my kinetic energy up at the top of the hill is 0. We've got this incline of 50 degrees, the coefficient of friction, so my mu is going to be 0.1 between the block and the incline. And we know it's going to move a distance, so this is going to be my distance here, is 1.5 meters. All right, we're going to be using energy terms in order to solve this. So let's take a look. We know that at the top, my velocity is 0. The energy at the top, unfortunately, I cannot say equals the energy at the bottom because we lost a little bit of this. We lost a little bit of our initial energy. So I need to find out how much work was done by friction, how much energy was lost by friction. At the top of the hill, we've got potential energy. So I know I have mgh minus, and we have the work done by friction. So that's going to be that frictional force times the distance equals the energy at the bottom. And at the energy at the bottom, we're going to have kinetic energy. So I'm going to put down 1/2 mv squared, which is going to get the velocity that we're looking for at the bottom. All right, at first glance, you look and go, darn it, I don't have the height. But if we have the hypotenuse, and what I'm really looking for is I'm looking for this height, isn't that simply going to be d sine of theta? So in fact, I do have the height, but I don't have the frictional force. So let's go ahead and see if we can do some substitution. So I have mgh minus my frictional force, and we define friction as being mu times the normal times the distance equals 1/2 mv squared. So on an incline, my normal, what does that equal? Well, it still equals mg cosine of theta times d equals 1/2 mv squared. Now, since I've simplified it this far, look at what I can do. I can actually cancel out the mass. So let's go ahead and solve. So I have 9.8 times my height, which was the distance, 1.5, times the sine, and my angle was 50, minus the coefficient of friction, which was 0.1, times 9.8, and that's the cosine of 50, times the distance, and the distance down the incline was 1.5 meters, equals 1/2 the velocity squared. Now we can solve for the velocity, which gives us a velocity of 4.54 meters per second at the bottom of the hill. So essentially all we're doing now is we're doing the same conservation of energy that we did before. The only thing is I now have to subtract the work done by friction from the total at the beginning. All right, we've seen how to deal with non-conservative forces. We'll see you next time.